Auzubillahiminash-shaytanir-rajim. Bismillahir-rahmanir-rahim. Assalamu alaikum. Welcome to the first lecture of week 3 of our subject ME220 Manufacturing Process 1. So in the last week we were discussing chapter number 11 of your textbook, that is metal casting processes. So in the last week we discussed some basic terms of the sand casting, and in the sand casting we were discussing the pattern making as well as the mold making. So we were discussing also the buoyancy force in the sand casting. One of the hazards during pouring is that the buoyancy force of the molten metal displaces the core, and we have discussed that before. But how to calculate that buoyancy force when we are pouring a molten material? So buoyancy force results from the weight of the molten metal being displaced by the core. As you have studied the Archimedes principle in your college, in your high school, the force required to lift the core of any object will be equal to the weight of the molten metal displaced by that body of will be equal to the weight of the volume or weight of the molten metal displaced by that body minus the weight of the body itself. So it can be written as the buoyancy force that is acting on the core would be equal to weight of the molten metal. Let's suppose if you have a flask here and you have any, let's suppose this is the core of your sand casting. So the volume, the weight of the molten metal displaced, this region, the molten metal is being displaced from this region. So the weight of that molten metal, that is equal to this volume minus the weight of this body itself, would be the buoyancy force acting on this body, right? So it says a sand core has a volume of 1875 centimeter cube and is located inside a sand mold cavity. Determine the buoyancy force tending to lift the core during pouring of a molten lead into the mold. So what it says, we are performing a sand casting which has a sand core, let's suppose this one, and the volume of the sand core is 1875 centimeter cube, and it is located inside the mold cavity as we have drawn here. Determine the buoyancy force. So the density of the sand is as per your book is 1.6 grams per centimeter cube. So the weight of the core will be equals to 1875, its volume, into the density. So we will get it's equals to 3000 grams, or we call it 3 kilograms. So the sand core, this one, weighs equals to 3 kilograms, but the molten metal that is being poured is the lead, and the density of lead is equals to 11.3 grams per centimeter cube. So the weight of the lead displaced by that body, by the sand core, is equals to the volume. Obviously the volume would be the same into the density of the lead. So we will have the value of 21188 grams, or we can write it as 21.9 kilograms. So the difference between them will be the buoyancy force. The difference between them would be 21.9 minus 3 kilograms, and it's equals to 18.9 kilograms. This is the weight of the metal or the lead being displaced, right? So the buoyancy, so the force that is exerted by this one, as we know that 1 kg equals to 9.81 newtons. So the buoyancy force exerted by this weight of the lead would be equals to 9.81 into 18.9, and that makes up 178.4. So this is the amount of the force that is being exerted by the lead on this core of volume 1875 centimeter cube. So this was the end of the sand casting, and now we'll begin with some other types of the expandable mold casting. Now we're going to start with some other types of expandable mold casting. So as versatile is the sand casting, as we know that the sand casting is versatile in terms of the geometry that can be designed, because it can cast some complex geometries, and almost any metal that can be melted can be casted using the sand casting method. So the other expandable mold casting are also as versatile as the sand casting, but they need some special requirements that we encounter sometimes, and there's some difference between them and the sand casting on the basis of composition of the mold material that we are using, or the shape of the mold, or the type of the pattern we are using. So although the basic methodology of all these types of expandable mold casting is same, but they do differ in some techniques, like the type of the material we are using for the mold cavity, or the type of the pattern we are using, or the shape of the mold itself. So some prominent types of expandable mold casting: the first one is the shell mold casting, or the shell molding. We have the vacuum molding, or the expanded polystyrene process. It's also known as the EPS. We have the investment casting, and the plastic and ceramic mold casting. So the common advantages and disadvantages for all the expandable mold casting is that we have discussed that before, that the expandable mold casting, because we can destroy the mold after each cast product, so owing to that we can cast some complex shapes, because we don't require to keep the mold intact, we don't require to save the mold, so we can cast some complex shape. And the disadvantage, the common between all of these, are because we are making mold every time, so that's why the production rate is slower compared to the permanent mold casting. So let's start with the shell molding. It's a type of the expandable mold casting in which mold is not a whole flask filled with the sand, rather mold is a thin shell held together by a thermosetting resin. So we know that we add resins and binders into the mold material to keep it intact, but in this case the mold is not the whole bulk sand, rather it's a thin shell and that is held together by the thermosetting resin, and that shell thickness is typically 9 meters or 3 by 8 inches. So how do we do that? In the first step, we make a match plate pattern. You know what the match plate pattern was? If you remember our previous lecture, the match plate pattern was like, we had a plate and both cope and drag were attached to this plate. There was some protrusion figure as well as a drag part was also there. Right? Both were assembled to a single plate to keep the dimensions close, or There shouldn't be difference in their alignment to keep the alignment as perfect as possible. Or we use the cope and drag pattern, in which we have separate plates for both cope and drag part. The cope part is attached to a separate plate while the drag part is attached to the separate plate. So we can have some cores or any other internal features. So in the shell molding, we have a match plate of the cope and drag pattern, and we heat the pattern in first step. We heat the metal pattern and place it over the flask, right? Place it over the flask, and that flask is filled with the sand mixed with the resin or the binders. Then we simply invert the flask and allow the sand mixed with the resin and the binders to lay down on this pattern, and we allow it to form a shell. So the layer of the mixture to partially cure on the surface and forms a hard shell. So there's a layer of mixture of sand and resin, partially cures and forms a shell over the pattern surface. Then box is repositioned into its original position. It is repositioned, and the remaining sand particles are allowed to settle down. Then this, in the fourth step, this pattern with the sand shell on its surface is placed into the furnace or oven. Then sand shell is heated in the oven for several minutes to complete the curing. Once it is heated for some few minutes so that it becomes hard, it is taken out of the oven and the shell is removed from the pattern surface. It is stripped from the pattern surface. Then we again perform the same steps for the second half of this mold cavity. The two halves of the shell mold are assembled and supported by this clamp as well as the sand mixed with the metal shots, and it forms a mold cavity. So once we pour the molten material here, we will get a product like this one. So there are certain advantages and disadvantages for this shell molding. The first one, the surface of the shell molding. The advantage is the surface of the shell molding is smoother than the conventional sand casting or the green sand mold, because we know that it has some moisture over it, so it causes some defects or the roughness in the surface. While in the case of the shell molding, it is placed in the oven to remove that moisture and to have some hard surface or a hard shell. Second one, because of this smoother surface, we have a good dimensional accuracy, and we can have tolerance as low as 0.25 millimeters from medium to small to medium parts. And because of this good dimensional accuracy, there's sometimes little or no machining. There's little or no requirement of the machining after the casting process. And as we don't require any machining, there's no waste material as well, because once you perform the machining, we are removing some extra material and it is removed as a waste. Then there's another advantage for the shell molding is that it offers good collapsibility. So once the material is allowed to cool down and it is solidified, it undergoes shrinkage, so the mold doesn't collapse. It allows the part to shrink while solidification, while cooling. And it can be mechanized for the mass production because of it has several steps involved, and it involves the metallic pattern here. So this kind of the expandable mold casting, the shell molding, is not justified for the small quantities, rather it is justified for the large quantities. So it can be mechanized for the mass production. Some common parts that are made using the shell molding are like gears, valve, bushing, camshafts. So these are general parts that are used in automobile that are made using the shell molding process. And the few disadvantages that we have discussed, it utilizes metal pattern, which is expensive, and owing to this expensive metal pattern, it is not justified for the small quantities. So it is mostly utilized for the large production. If we see here, they have some, you can say, with a body with some fins like a heat exchanger. So you can see we have multiple shells here, and it is being casted. From this figure you can see the surface smoothness that we achieve in the sand cast in this shell molding. While in the normal sand casting we have the surface roughness in this range like this one, but in the case of the shell molding it is somewhat smoother, much smoother than the conventional green sand mold casting. Then the second type for this expandable mold casting is the vacuum molding. So the second type of the expandable mold casting is the vacuum molding, and it is also known as a V process. It was developed in 1970s in Japan. One of the unique thing about this kind of the molding process or the casting process is that instead of using the binders in the mold sand or the mold material, it uses the vacuum to keep the mold intact. So how do we perform the vacuum molding? We have a match plate or a cope and drag pattern with some vents within the pattern. So we create a vacuum here, and we place a preheated plastic sheet over the pattern, and so it sticks on the surface of the pattern and remain intact because of this vacuum. Then we place a flask and fill it with the sand and sprue and the pouring cup, and we also apply the vacuum. We also create the vacuum, use a vacuum pressure here so that the sands remain intact, and also we keep on applying the vacuum here as well. Then we place another plastic sheet over the flask, and we keep on applying the vacuum here so that it is covered from the top as well as it is covered from this plastic sheet as well. So when it settles down, we will terminate this vacuum and remove the pattern so that it leaves behind the vacuum. We leave behind the mold cavity with a plastic film stick onto its surface here, right? Then you make the drag part of this mold cavity, and we assemble them together, and we keep on applying the vacuum pressure so that the sands remain intact. So once we pour the molten material into the mold cavity, this plastic film burns away, and the molten material is allowed to solidify. So when it is solidified, we simply remove the vacuum pressure, vacuum is withdrawn, and we can take out our part. One of the advantage of this method is that the sand used here in this casting can be reused instantly because there's no riser or the binders or thermoset binders here in this kind of a sand. Rather, it was intact by using the vacuum. One of the advantages is that it's a relatively slow process and cannot be easily mechanized. So it is difficult to mechanize or automate this kind of the molding or the casting process. That's why it is, because it is slow. Then there's another type of the expandable mold casting is the expanded polystyrene process, or it's also known as the EPS, as I told you before. So in this type of casting, we have sand mold packed around the polystyrene foam pattern. So what happens? We take a huge foam of EPS, expanded polystyrene, and we machine by using the machining process, various tools like lathe machine or milling or the drilling. We make a pattern. Here. Let's suppose we want to cast a product like this one. So we machine a pattern out of this foam, and we packed sand around it. So we place this pattern into the large flask. So this pattern will be placed here. So we will place this pattern within the flask and we will fill this flask with the sand. We will pack the sand around the polystyrene foam pattern. We also machine the sprue and the runner within this foam pattern. So once we pour the molten material, this foam vaporizes, and the foam itself becomes a cavity in the mold because it has a sand around it. So this foam itself is a cavity because once we pour the molten material, it vaporizes, it vanishes. So that's why it is also known as a lost foam process, because we loses the foam, it vaporizes. It is also known as a lost pattern process because this foam was itself a pattern, the mold itself was a pattern. And it is also known as the evaporative foam process because it vaporizes, and it is also known as the full mold process, right? So there are several names for the EPS process. So the pattern, as I said before, the pattern consists of the sprue, runner, riser, and mold. So all the features of the mold cavity are included in the pattern, and this pattern vaporizes as soon as we pour the molten material. So pattern itself is a mold cavity, pattern itself is a cavity within the sand. As there is no need of removal of pattern after sand packing, so there is no need to divide the mold in cope and drag. The unique feature of this about this casting process is there is no cope and drag in this kind of a casting, because there is no need to remove the pattern from the cavity. Pattern is coated with a refractive material for a smoother surface and better resistance. So we coat this surface of the pattern with some refractive material, because this surface will be in contact with the sand and they will make the surface of the part as well. So we coat it with this refractive material to get the smoother surface in our final product, and also for some resistance to the temperature, because we want it to sustain some amount of heat for some period of time, so that uh, the molten material will have enough time to enter into this cavity, the pattern cavity, and fill this space completely. So molding sand that we use here, the molding sand around this pattern, consists of a bonding engine, but in some cases it's dry, right? Although we use normally we use some risers and thermostatic binders, but in some cases we also use the dry sand in the EPS process. So some common advantages for this one is pattern need not to be removed, right? As we discussed before, there is no need to remove the pattern because pattern itself is a mold cavity in this EPS process. Second one, all the features such as gating system, riser, core are embedded in the pattern, so there is no need to design them separately. Everything is machined into the pattern. There is no need to design it separately because there is no removal of the pattern required. There is no formation of mold required separately, so the production time is less. So this kind of the casting process can be used for mass production, and it is used in the automobile industry for casting the automobile engines. Another disadvantage for this kind of a casting process is because we need a new pattern every time, so it has some economic burden. So it's economically somewhat expensive because we need new pattern every time. Rather, it is very favorable for the mass production and for complex shapes. So if we see some practical demonstration or the animation for this casting process, as we have the lost foam in the bulk form, and it is machining using any steam injection or any other machining process. So it is machining out the pattern from this polystyrene. Now the pattern is ready. We are coating it with the refractive material, and the purpose of the refractive material was to have better surface finish and to resist the temperature. This is the flask. We have placed the pattern into the flask, and we have added the sprue and the riser and filling it with the sand. So now we are pouring the molten material, and because of the high temperature, this foam vaporizes. This is the refractory coating what was left from the original pattern. The original pattern was vaporized, only the refractory coating was there. This is the final finished product. Another type of the one of the type of the expandable mold casting is an investment casting. The word invest means to cover completely, and again it refers to not to the final product, but it refers to the mold cavity itself, like in the case of the vacuum process, vacuum molding. So in the case of the investment casting, we usually have two patterns. We make two patterns. One is the master pattern, and this master pattern is used to make another pattern made up of wax. This master pattern is used to make a wax pattern. This is how the process begins. We make a master pattern, and this master pattern has all the shrinkage allowances and the machining allowances for the pattern as well as for the final product. And using this master pattern, we make another pattern that's called a wax pattern. And you would understand why do we make master pattern in the wax pattern. Then we take this wax pattern and we dip this wax pattern into the slurry of our refractory material. So we have a pool of any refractory material with some fine grain so we dip this wax pattern into the slurry, fine grained slurry of a refractory material, and we allow it to settle down onto the surface of the pattern, wax pattern. Then it is inverted and it is heated so that this wax melts out of this shell of the refractory material, and it leaves behind a cavity made up of the refractory material. So we simply pour the molten material into this cavity of the refractory material and allow it to solidify. Once it is solidified, the refractory coating mold cavity can be broken away from the part surface, and we can take out our product. So this is how we perform this process, and it is called investment casting process because the invest means to cover completely. So we are covering this wax pattern with the refractory material completely. We are dipping into the slurry of the refractory material. That's why we call it the investment casting. And it is a very precision casting process because it gives very high accuracy in terms of dimensions, and we can cast product with great complexity in shape as well as some intricate details. We can in this kind of casting process we can cast multiple products. So what we do, let's suppose if you are making cups like this one and you want to make multiple cups, so we'll make a sprue of the wax and we will attach the multiple mold cavity with this main sprue, so that once you pour the molten material, it will fill up the cavity of all those cups. So we can cast multiple products by making a pattern tree. This is called a by making this pattern tree. So this wax sprue will help us to connect all the molds together with this main sprue, and we can supply the molten material. So there are certain advantages for this kind of the casting process. The first one is it can cast with great complexity, complex shapes, and intricate geometries are possible. Complex shapes and intricate geometries can be casted using this kind of a process. The another advantage for this, it has a good dimensional accuracy. Right? So the dimensional tolerances even range from 0.075 millimeter. And probably you remember in the case of the vacuum process we have dimensional tolerance of 0.25 millimeter. So it is even better than the vacuum process we have now, 0.075 millimeter. Another advantage for this, it has a good surface finish. And the wax can be reused. But it's a relatively expensive process. So this one is expensive process because we need to make a wax master pattern. Then we make from that master pattern we make a wax pattern, and from that wax pattern we make a refractory mold cavity, and then you get the final product. So it's relatively expensive process. It cannot cast a very large product, rather it can cast small or somewhat medium sized product that can weigh up to 75 pounds. So parts that require the complex shapes where intricate geometries can be cast, such as some parts like that can be casted, or the common products for the investment casting include the turbine engines, or we have jewelry, because they do have some intricate details, dental fixtures, they are made by the investment casting, and so on and so forth. So this was the fourth type of the expandable mold casting. Now the last one is the plaster mold and the ceramic mold casting. Before that we have an animation for the investment casting. So this is the master pattern, and wax is injected into the master pattern, so to make a wax pattern out of it. So there are multiple parts that are attached to the wax pattern with the main screw of the wax pattern, and then the whole pattern is dipped into the slurry of the refractive material. It is inverted and heated so that the wax melts out, leaving behind the ceramic mold. So once you have the ceramic mold, we pour the molten material into it so that it fills the whole cavity and allow it to solidify. After the solidification, we simply break the refractive material mold and take out the product. So we can see the accuracy of the dimensions and the intricate details in the product that is obtained using the investment casting. So the last type of the expandable mold casting is the plaster and the ceramic mold casting. They are similar to the sand casting. Only difference is the composition of the mold material that we are using in the case of the plaster and the ceramic mold. So in the case of the plaster mold casting, we use the plaster of Paris as the mold material, and the plaster is mixed with the water and it is poured over a plastic or the metallic pattern. So let's suppose we have the metallic pattern here. So we'll make the mixture of plaster and the water and pour it onto this mold cavity so that it flows over this pattern and allow to settle down with all the details of the pattern. In this case, wood patterns are not preferred because there is a contact with the water, so the moisture will affect the shape of the wood. So because in this type of the sand, in this type of the expandable mold casting, the mold material initially is like a fluid, so it flows over the each and every detail of the pattern, so that it ends up capturing all the details of the pattern. So it has some good surface finish with the great details. One of that some disadvantages for this kind of the casting process is the curing, because it slows down the process. It takes some time. Not all moisture is removed from the mold. There is some moisture left in the mold cavity, in the mold material, which ends up affecting the properties of the cast product. And the mold strength lost when and we need to have some moisture in our mold cavity, although moisture is not favorable. The moisture is not favorable for our product, but we need in this case we do need the moisture in our mold material. Why is that so? We know why moisture is not favorable, but why do we need the moisture in our mold material? Because once it becomes too dehydrated, if we remove so much out of the moisture, the plaster will ultimately lose its strength and it is a possibility that it will fracture. One of the disadvantage in the plaster mold casting is that it's not permeable, so it restricts the flow of the hot gases outside of the mold cavity, so which ends up forming porosity in the final product. To overcome this problem of lack of permeability in the mold material, there are multiple ways. We evacuate air from mold cavity before pouring. So what we do, once we have the mold material in the mold cavity, we create a vacuum, or we remove the air from the mold cavity and pour the material afterwards. Another method is aerating the plaster slurry at the mold cavity, so that the resulting harder plaster contains finely dispersed void. And there's another method that's called the anti-Hodge process. There's another method that's called the anti-Hodge process, in which we have the 50% of sand mixed with the 50% of the plaster. So we have the 50% sand and the 50% plaster. So we have the surface finish of the plaster with some permeability of the sand. So we end up having benefits or the advantages of both sand and the plaster. So this is the end of the types of the expandable mold casting. We now will move towards another section of the casting process, that's the permanent mold casting. So as we discussed time and again, the basic difference between the expandable and the permanent mold casting is that in the expandable mold casting we end up destroying the mold after every cast product, while in the permanent mold casting we don't destroy the mold after every casting process. Rather, each mold cavity can be reused many times until it wears off or it is affected by any other means. So this is the end of this lecture. Should you have any question, you may reach me at the Google Classroom, or you can directly email me. In the next lecture, we are going to discuss the types of the permanent mold casting.